Okay, in this video, I'll be explaining and showing off the Mathematica document I used to numerically solve and then plot the equations of motion. And I've done this in two coordinate systems, polar and then three-dimensional Cartesian coordinates. So starting here, this is the gravitational constant, which is just used throughout the document in the code, and here's the polar equations of motion, and this is how they're solved. So this function here is basically it returns the solution to the numerical solving of the polar equations of motion here, and it returns a solution for these different arguments. So you input the arguments, which are initial distance. They're basically boundary conditions which are needed for the numeric solving of the differential equations. Yeah, they're basically boundary conditions. So you input the boundary conditions, and then this function here returns the solution, which then can be converted to Cartesian equations, then plotted. I'll get back to this equation in a second. So this visualization here, basically these sliders let the user input boundary conditions, and then the visualization shows the solution to the equations of motion using these boundary conditions. And we can have a look at the code here. So this is the solution, and basically this bit of code here takes the solution and then converts it to Cartesian coordinates, and then the Cartesian coordinates are plotted here, and then here's the different sliders which are used to manipulate the arguments. Okay, the problem with this is it's very tough to get arguments which reflect actually a physical body in real life. So I can't really compare this orbit to the orbit of the Earth, because I'd have to find out all the different initial conditions, which takes a long time. So to get around this, I use the Mathematica database, which basically I can use to retrieve the orbital elements, and these orbital elements via the equations, which are here, are then converted into boundary conditions, and these boundary conditions reflect real life. So then I can compare them with real life. I can compare the solution to real life. Here's this function basically takes the standard gravitational parameter, the distance from the central body to the orbiting body, semi-major axis, eccentricity, and just takes all these arguments and then converts them into the angular velocity, which is used for a boundary condition. The reason why there isn't more equations to create the other boundary conditions, such as initial distance and radial velocity, I've explained that in my investigation, my documentation, so I won't go into detail. Anyway, here it is. Here's the visualization that represents real life, and basically the user they pick a planet, and once the planet is picked, Mathematica goes to the internet, its database, retrieves the orbital elements, and then plots the solution for these the boundary conditions created by the orbital elements, as you can see. And this is kind of quantitative data which I can compare with real life now. So and it's a lot better than the above here. And I've added in here a mass scaler, so I can scale up and down the central body, just changing the intensity of the gravitational field really, and I can then immediately see how the orbital path will be changed. So if the mass of the Sun was 4 times greater, Jupiter's orbit would be a lot more eccentric. Okay, I'll just quickly show the code. As you can see, it's basically identical to the above, except the arguments for psolve are now objects taken from the mathematical database. Okay. Now going down to the Cartesian equations. Again, this is another function similar to the psolve, which is used to numerically solve the Cartesian equations of motion. So this is a vector equation now. So the boundary conditions are different elements of the velocity and position vector, as you can see, and the equations needed to create these boundary conditions they're a little more numerous. So I need one equation to create one element of each for the vectors here. So this corresponds to this, and this corresponds to that. And these equations are used again just to create a real physical quantitative result. Again, here's a visualization whereby I can directly change the boundary conditions and see how it changes. And now that we've got a third dimension, it's a little more interesting. I can change the initial z distance. So now you can see the orbit is almost 45 degrees, and things like this. Anyway, here it is, similar to the polar one, to the polar user-defined visualization. Anyway, going down to the real world one, I've also added an option here whereby you can change the center of mass. So these are also presets. When I click Betelgeuse, the code goes to the internet, retrieves the mass of Betelgeuse, and then uses it as an argument for the numeric solving. Now that we have 3 dimensions, you can see that Pluto's inclination is quite large in comparison to in the Earth. It's in fact it's got the greatest inclination, so it's most tilted from the ecliptic. Anyway, again, it's got all the same sliders as the polar equation. And if we take a look at the code, you can see it's a lot more complicated because it's got more components, boundary conditions, and each of these boundary conditions requires a function to convert the orbital elements to the boundary conditions. But I still think it's a rather elegant way of getting this data into the visualization. Okay, so that concludes this section.